In this video, I'd like to introduce the idea of computing volume by slicing. And this is something we'll continue to look at in the next few videos, but essentially each individual video will be devoted to a particular shape. So to start with, let's look at a cylinder. In particular, we have a cylinder of height 10 and radius 2, and we want to use slicing to find the volume. So when I say we want to use slicing, it's the same idea that we have when we just started talking about Riemann sums in the beginning. So we've seen, for instance, if we want to find the area under a curve or between curves, what we can do is essentially slice the interval into rectangles of equal width. And our goal then is to approximate the area first by adding the area of each of those rectangles together. And then, as we've seen when we define the definite integral, if we send the number of those pieces to infinity, then we get the exact area. So a similar idea here, but now we're thinking about 3 dimensions. So let's assume that we want to slice this horizontally. So think about that as parallel to the base. Of course, we could go through this vertically, but I'm just going to focus on the horizontal idea. And what we want to consider then is, first of all, when we do so, what kind of shape do we get? Because what I want to do is break this up into n slices such that I can add the volume of each of those n slices together and give me then the volume of the entire cylinder. So let me use a different color. So let's consider a very thin slice that I make on this cylinder. So I cut through it horizontally, and just like we have a width for a rectangle, I'm going to have a little thickness here in my slices. So if I think about my vertical variable here as delta h, then, as h, then this thickness is going to be delta h. And so that has a very similar role to delta x that we saw with our original Riemann sums. And to begin with, what I want to consider is finding the volume of one of these slices. And in order to do so, we have to pay very special attention to what kind of shape we get out of these slices. And we're going to see in our different examples, we can focus on all different kinds of relationships here. But to be clear, I have this kind of larger view where we can see one of these slices. But if I'm thinking of one of my slices, the kth slice, well, we know that we're going to get a very, very short cylinder. And I say very, very short because we know that we usually choose many pieces. So the height of this cylinder is delta h, and the radius of this cylinder is exactly the same as the radius of the original cylinder. So what you want to try to envision is that we split this up into those n little cylinders, and then it makes sense that if I were to add the volume of those n cylinders, then the result would give me the entire volume that we're looking for. I will point out I'm starting with this example intentionally where we can see that there's a perfect match to adding up the volume of the slices to the volume of the entire shape. We'll see when we look at a hemisphere and later a cone that we truly do get an estimate when we have finitely many pieces that we're looking at. And therefore, sending the number of pieces to infinity then is incredibly valuable for giving us the exact answer. So in this example, it is true that simply the sum alone, without turning it into an integral, would give us the exact volume. But what I'd like to establish is at least a process. So just like we've done when we were trying to construct the definite integral from our knowledge of Riemann sums, same idea here. Let's think about how we can build this up. So the first thing I would identify is what is delta h. So just like we've seen before, delta h is going to be the length of our interval, and here that means the length of our interval of h values, which is 10, divided by the number of slices, which we're just going to say is n right now. Once we've found delta h, then we define h sub k as a plus k delta h, just like we've done before. Again, a is the smallest value in our interval, so if we're looking at our interval of h values, the smallest value will be when we're at h equals 0, and the largest value would of course then be up at the top when h is 10. So in this case, my A value is 0, and K times delta H is 10K over N. So once we have this, if I want to now look at the volume of my kth slice, again, I come back to this picture here where we saw that the kth slice is going to be a cylinder, and we're going to use then that the volume of such a cylinder will be pi times the radius, 2 squared, times the height of the cylinder, which is delta H. So we're getting here 4 pi delta H is going to be the volume of one of those cylinders. Then if I want to think about the volume here, again, it is exactly equal to the sum, but I'll say as we look at different shapes in general, we get an approximation of the volume by then adding up the volume of each of our K slices. And in doing that, we now get this sum. So the nice thing about this is now I'm at a point where I am interested in thinking about what integral we would get if we were to send n to infinity. And in the situation where we're not getting an exact value of the volume from adding up the slices, by sending n to infinity and constructing the integral, that has the advantage that we are getting the exact volume. So what we would be able to say is that v is exactly equal to the limit of our Riemann sum that we constructed here. And the advantage of having set up this Riemann sum is now I can really see what the integrand is going to be. So in particular, I see that my integrand is going to be the constant function 4 pi. The reason is we think about where everything goes. So delta H now becomes dH. That leaves the 4 pi, which is just a constant function in this case. And then the other thing I really want to focus on here, a common mistake I see is then translating into the bounds on the integral. The 1 and the n are not the bounds on the definite integral. So 1 and n are dictating the values that k, our index, ranges over. So that only has significance in our sum when we're actually marking off which slice we're on. Instead, when I want to fill in the bounds on my definite integral, I need to really pay attention to the fact that this is an integral with respect to h. And again, come back to the context here and see that h is the height. And as we already established what I've written in red here, the smallest value of h is 0, the largest value of h is 10. So those are the values that I plug in here. And so now I'm at a point where I can anti-differentiate. We get 4 pi h, where h ranges from 0 to 10, and we get that our volume then is 40 pi. And like I said, we're going to go through this same exact kind of setup here that we've established, finding the change in h or whatever the variable might be, getting this to a point where I can then find the volume of a particular slice, add those together, and then work our way toward setting up a definite integral to get the exact volume. And one thing I'll really emphasize in the other videos is the significance of the fact that in this example, the volume of my slice was constant. So as I moved up the cylinder, the volume of the resulting slice did not change. We're going to see that that doesn't always happen, and in the next few videos, we'll have to see what added difficulty that might present and how we can deal with that.